No, Yankee. See, it was tough last year.
Exactly.
My code is still running. It's been running for like 30 hours. I guess I don't have a modern CPU. Yeah, I'm definitely going to use a GPU.
Like, you know someone who has one, or are you gonna?
No, I mean, I think I'm gonna set up a VM on I'm gonna either use Colab, which someone said on Piazza. Well, Colab is free in general. It's like always free. But it's kind of annoying to use because when I used it when I took machine learning, it would often disconnect due to inactivity. Even though it would only be inactive for like 10 or 15 minutes. Like it literally needed a force to balance. Or I might just set up a So I probably spent like a cumulative at least like 1 hour now.
Is the microphone issue fixed?
Like maybe 5 minutes here, 5 minutes there, because I keep trying. There's like a certain time that pops up with like the stats. Yeah. Because I'm an idiot and I didn't disable this printing. So like, oh, you're printing it. I know. Well, I wonder how much it really slows down. It might print like 1,000 times, like every 10,000. I'm sure it slows it down. Hopefully it's not like terribly bad. Yeah, it has to do an interrupt, like multiple interrupts every single character. Yeah, that you take in class. Yeah, man.
Is there a black marker?
All these modes switch.
Oh, right here. Okay, good.
Yeah, I'm an idiot. I should have played. I was like,
all right, let's get started. So after our sort of power company enforced vacation last week, we're going to resume with our regularly scheduled program. And because we had to miss one lecture, what I'm going to do is I'm going to actually cover the material that I was supposed to cover last week on Wednesday today. And then the lecture that was intended to be today, you'll actually watch online. So I made a post on Piazza about this. Basically, the lecture that was supposed to be taught today is the variational inference lecture, which is the one that is probably kind of the most tangential to the main course material. It doesn't cover anything about reinforcement learning. It actually covers amortized variational inference techniques, which some of you might already know about. But if you don't know about them, then it's important to watch that lecture from last year that I posted on Piazza, because I'm going to assume that you already know that material when I cover control as inference on Wednesday. So I'm going to skip the variational inference lecture, and those of you that are not familiar with variational inference should definitely watch the lecture from last year that I posted on Piazza. Today I'm going to cover the material that was supposed to be done last week, and then on Wednesday I'll resume with what was supposed to be the Wednesday lecture this week. Okay, so other than that, the only other logistical note is that homework 3 is out. That's going to be due on October 21st as usual. And remember that homework 3 is a little bit more heavyweight than usual because of the Q-learning and image-based Q-learning assignments for Atari. Those will take a while to run. If you don't have a GPU, they might take as long as an entire day to run. So do make sure to get that stuff implemented and all set up early. You can definitely debug it on much simpler tasks like Lunar Lander, which don't take nearly as long. But the final thing will take a while to run, so get that done early so that you have enough time for the training run to complete. All right. Today's lecture. So last time we covered model-based reinforcement learning without policies. So we mostly focused on how do we learn good models, and we saw that we could have kind of the reinforcement learning, the model-based RL version 0.5, 1.0, and 1.5, and so on, like kind of different versions of of this algorithm that all differ in essentially in how they collect the data that is then used to train the model. But the recipe for control was always the same. You train up your model to be as accurate as possible on the data you've collected so far, and then you plan through that model using any of the planning or control algorithms that were covered the week before. Today, we're going to talk about another way to approach model-based reinforcement learning, where instead of planning through a model, we're going to actually use that model to try to recover a policy, which is going to look a little bit more like the model-free RL algorithms that we covered in the first portion of the course. So we're going to talk about algorithms that can use models to learn global policies, the kind of policies that we're all familiar with. We're also going to talk about algorithms that use models to learn what we could call local policies, policies that are not meant to be big neural net policies that are correct everywhere, but that are meant to be effective in a narrow region of the state space. And I'll explain a little bit for why this might be a good idea. And then in the last portion of today's lecture, we're going to discuss how these local policies can actually be combined back into the global policies that we're more used to. And if this doesn't make much sense now, I think it'll be a lot clearer why this is a good idea later in the talk. But we'll cover methods like guided policy search and policy distillation. Okay, so the goals for today's lecture will be to understand how and why we should use models to learn policies, and then understand this whole global and local policy learning stuff. So in a sense, this lecture is kind of really covering two slightly separate topics that are still quite related. The first one is using models to learn policies, and the second one is this connection between global and local policies, which is often used in model-based RL, but can also be used in purely model-free RL methods, as we'll see at the very end of the lecture. Okay. So last time I talked about model-based reinforcement learning with planning or optimal control algorithms. And in particular, the final method that I arrived at was this model-based RL that I called version 1.5, which is also called model predictive control, or MPC. So this is the method where you start off by collecting some data. Then you learn your dynamics model F on that data. Then you plan through your dynamics model to choose your actions using any of the methods from the week before, like MCTS, LQR, random shooting, whatever. Then you execute the first action in that plan, and then you observe the resulting state S prime. Then you append the tuple SA and S prime to your data set D. And then you repeat this, so you do this every time step. And then maybe every n steps, you update your dynamics model with all of the data gathered so far. So this was the basic recipe for sort of the final model-based RL algorithm that we arrived at the end of the lecture last week. And this is, in fact, the method that you will be implementing for homework 4. So homework 4 is currently being prepared by the TAs. It's almost ready. And when it comes out, this is what it's going to have you do. However, if we think back to our discussion at the beginning of this kind of model-based RL portion of the course, we learned about three kind of different regimes. We learned about the deterministic open loop case, the stochastic open loop case, and the stochastic closed loop case. And as a reminder, the difference between open loop and closed loop is whether or not the agent actually plans to react to future observations. And this distinction is actually very important. So in the open loop case, what the agent thinks is happening is that it gets to observe the initial state, then formulate a complete plan consisting of a sequence of actions, and then has to commit to that plan. Now, in reality, the environment might still allow the agent to plan again at the next time step, but when the agent plans, it does not realize that it will be allowed to change its mind. Which means that the optimization problem that the agent is solving is to maximize the expected reward conditioned on a sequence of actions. And as we learned before, this can be highly suboptimal in some cases. So the example that I gave when I discussed this the first time was that if I were to tell you that I would give you an algebra quiz at the end of this lecture, so that's S1, so the knowledge you observe is there will be an algebra quiz. And then I ask you to give me the set of answers that you would write down on your answer sheet for that quiz. So that's your plan, A1 through AT. This would be a very difficult control problem, because without having observed what the quiz is, you can't really tell me what a good set of answers is. So you might know all about how to solve algebra quizzes, but before you've actually observed the next state, you can't commit to a course of action that would result in a good outcome, even though you know basically how to solve this kind of control problem. Okay, so the alternative to the open loop setting is the closed loop setting. And the closed loop setting looks a lot more like the kind of classical reinforcement learning problems we've seen before, where now you have a policy inside of this distribution, so you have a joint distribution over states and actions rather than a distribution over states conditioned on actions, and you're optimizing over the policy. So now, as you optimize over this policy, you can essentially reason about how, well, if I observe this state, then I'll take this action. If I observe this other state, then I'll take this other action. So instead of committing to a single plan, a single sequence of actions, you can commit to a strategy that says, if this happens, do that. If this other thing happens, then do this. And you can do better if you're allowed to do closed loop control. And of course, closed loop control includes the kind of stuff that we discussed in the first portion of the course, these kinds of heavyweight neural net policies that attempt to output a good action in all parts of the state space, which I'm going to call global policies. But it also includes kind of a simpler kind of closed loop control, where maybe you have a policy pi that is good in some region around a trajectory. So for example, when we talked about LQR in the optimal control lecture, we saw that LQR doesn't just produce an action, it actually produces a feedback matrix that I called capital K and a feed-forward term called little k. So you could imagine that as the state changes a little bit, this feedback matrix will slightly vary the action and provide some degree of resilience to changing states. So this is the kind of thing that I would call a local policy, something that gives you appropriate feedback in a narrow region around the particular plan that you constructed. Both of these are closed loop controllers. This one is a closed loop controller in a very large chunk of the state space. This one is only going to do reasonable things in a narrow part of the state space. And we're going to talk about both kinds today. Okay, so this was mostly recap, but does anybody have any questions about this? Okay. So let's think about how we can use models to train policies. So we saw that there's some virtue in training policies as opposed to committing to individual plans. One of the things we know how to do is we know how to do backpropagation, and we know how to do gradient descent. We also know how to do gradient ascent just by changing the sign from a minus to a plus. So can we backpropagate into a policy and do gradient ascent to maximize reward? So we can construct a little computation graph. You can do this in TensorFlow or PyTorch or whatever your favorite numerical optimization package is. You can construct some nodes for your reward function, some nodes for your learned dynamics, and some nodes for your policy. And let's assume that they're all deterministic for now. You can handle stochastic dynamics and stochastic policies too. It's just a little more complicated. Everything in this computation graph can be made differentiable because you're learning your dynamics. So your dynamics is maybe some neural net. You're learning your policy. Maybe your policy is also a neural net. And if all you want to do is maximize the reward, you can simply set the output of your computation graph in TensorFlow or PyTorch to be the sum of rewards at all the time steps, call dot gradients on it, and get the gradient of the total reward with respect to your policy parameters. And then backpropagate through it. Does anybody have any thoughts about whether this is a good idea? For or against? Does everyone want to raise your hand and tell me either why you think this is a good idea or why you think this is not a good idea? How many people think that this would work well on the kind of problems that you're doing for, like, let's say, that you did for homework 2? Raise your hand if you think this would work well. Raise your hand if you think this would work poorly. Okay, so there's some ambiguity there, and some of you, I think, we're kind of trying to signal your posterior probability by raising your hand for part of the time period and then putting it back down again. So you can sort of surmise that some people are like, you know, 50, 70%. So let's say that this process, you know, this computational graph extends over however many time steps are in your episode. So let's say that your episode is very long. Maybe it's 500 time steps or 1,000 time steps. What might go wrong when I build this computation graph and call dot gradients on it? Any hypotheses? Yes.
vanishing or exploding gradients?
Right, so you could get what's called vanishing or exploding gradients. What are vanishing or exploding gradients? Well, imagine what the derivative of the total reward with respect to this first action would be. The way that you compute derivatives with backpropagation is you essentially apply the chain rule. When you apply the chain rule, what you're doing is you're multiplying together a whole bunch of Jacobians. And if there are 500 time steps, you're multiplying together 500 Jacobians. Now, when you multiply together 500 different matrices, the eigenvalues of those matrices have a very profound effect on what the resulting product looks like. So if they tend to have eigenvalues less than 1, when you multiply them all together, their product will have eigenvalues close to 0. If they have eigenvalues greater than 1, when you multiply them all together, their product will have eigenvalues close to a very, very big number that will overflow your floating point computations. So that's called vanishing and exploding gradients. So the basic procedure, as you might have already anticipated, is you run your policy, you collect some data, and then instead of planning through your model F, you backpropagate through F into the policy to optimize pi theta. And the trouble with this is that you get big gradients over here, or vanishing gradients if your Jacobians have eigenvalues less than 1, and you typically have very, much more reasonable gradients towards the end. And this is very much also like the problem that we saw before with shooting methods versus collocation methods. So if you have this big, long trajectory that results from taking some action at the beginning, changing the action at the beginning will sort of wiggle that trajectory in really big ways far outside of the region where the linear approximation obtained via the derivative is reasonable. OK, so vanishing and exploding gradients in the parlance of deep learning, this kind of sensitivity issue in the parlance of optimal control, but one way or another, this basically amounts to very poor numerical stability. So you have kind of similar parameter sensitivity as shooting methods, but you no longer have convenient second-order LQR-like methods for doing this because your policy is some complicated nonlinear beast, and you really have to rely on first-order optimizers, which are not good for trajectories. And it's kind of a similar problem to training long RNNs with backprop through time. So that's where the term vanishing and exploding gradients comes from. It comes from study of recurrent neural networks, where people figured out pretty early on that if you have long temporal structures like this, unless you do something very clever, it is very difficult to get meaningful derivatives over here with respect to a loss at the end over here. Now, in the world of deep learning, when we have to do backpropagation through time, we typically have some tricks at our disposal. For example, we can use a special form for the functions that are on the backbone of this temporal chain. In particular, we can use structures that result in nice, well-conditioned gradients. That is, structures whose Jacobians tend to have eigenvalues close to 1. So the LSTM is one example of this. Various temporal attention schemes are also good examples of this. While this works very well for training recurrent neural networks, it's unfortunately not really an option for us when we're doing model-based reinforcement learning, because we don't actually get to choose this F in the sense that this F really needs to just mirror the dynamics of the real world as closely as possible. So it needs to be trained to produce next states that would actually occur in reality, and the real dynamics might have very ill-conditioned Jacobians. So we could, of course, sacrifice the fidelity of our model for the sake of making it more differentiable, but then we'll get policies that don't necessarily do well in the real world, but only do well under this made-up model. If we instead make the model as accurate as possible, it might have Jacobians that are very ill-conditioned. OK, so what are some solutions to this? We saw that it's kind of tough to backpropagate through this whole thing, so somehow we need to do something a little bit better. Maybe something that is not first order, maybe something that avoids backpropagation altogether. What can we do? What are some ideas? Do you guys have any ideas about how we can use our models to train policies without these nasty products of lots and lots of Jacobians? Yeah?
Do like a ResNet type approach where you pass in like identity plus the model, the dynamics model?
Mm-hmm. So the answer was, well, maybe we can do sort of a ResNet-like approach. This kind of makes sense in some cases. Like, for example, what if you're controlling some real-world physical system that's modeled as a collection of rigid bodies? For a lot of physical systems, a very convenient type of model is like a partial differential equation model. So instead of modeling, st plus 1 as a function of st80, you model s dot. And then you say, st plus 1 is st plus delta t times s dot. And now that will have a dominant diagonal, which makes sense for some kind of dynamical systems, but maybe doesn't make so much sense for other dynamical systems. Like, for example, what is this Atari games? Atari games probably aren't well modeled by that kind of thing. Any other ideas? Here's a thought. When we learned about policy gradient, did we need to do backprop through time for policy gradient? Somebody else? Somehow policy gradient avoided backprop through time. So this is going to be the first class of methods that I'm going to cover, actually. It's a little peculiar. So the idea here will be to use derivative-free or model-free RL algorithms, but actually using the model to generate synthetic samples. And this seems weirdly backwards because we went through all this trouble to acquire a model. Like, the whole point of model-free was that we didn't need a model. Now we went through all this trouble to acquire a model, and now I'm going to tell you, and let's just go back and do the model-free stuff. And we'll just use the model to sort of generate fake synthetic experience. So this seems weirdly backwards because we did a bunch of work to get away from the model-free stuff, and then we're going to go right back there again. But it actually works very well. It's essentially a kind of a model-based acceleration for model-free RL, and there are a number of methods that do some variant of this. And there's actually good reason to believe that this might actually be a good way to use a model. So I'll discuss that a bit in the first part of the lecture. And then in the second part of the lecture, I'll discuss an alternative class of approaches which use policies that are simpler than neural nets. So when we talked about LQR the week before last, we saw that for very simple policies, specifically for linear policies, we could actually construct a dynamic programming algorithm that constructs the policy incrementally from the last time step to the first, and the corresponding method is actually very similar to Newton's method, making it a second-order optimization procedure. Turns out that second-order optimization, if you can do it, mitigates many of the problems with these products of ill-conditioned Jacobians because it essentially preconditions your gradient with exactly the right preconditioner. So if you can get away with doing a second-order optimization, which you usually can't if you're doing neural nets, but you can if you have very simple policies, then you can overcome these issues. So you could do what's called LQR FLM, linear quadratic regulators with fitted local models. So that's if you don't know the model, you fit the model and then do LQR. That gives you local policy, so it doesn't give you a neural net policy, but you can then combine these local policies into a global policy to solve more complex tasks. So I'll discuss that in the second half of today's lecture. But first, let's talk about this oddly backwards idea of using model-free optimizers with models. Okay, so to try to understand what's going on here, let's look at the form of the policy gradient. So this is our favorite equation from this course, from the first half of this course. This is the policy gradient expressed in the grad log pi times q hat kind of notation. And now that we've talked about backpropagation through dynamics, one of the things that you might notice about this equation that's quite appealing is that you never have to actually apply the chain rule. You never have to multiply the derivative of the next state given the current action by the derivative of the current action with respect to the policy parameters. That might first seem a little peculiar, right? It's like, how do you differentiate a sum of rewards over time without actually having to backpropagate through time? But that's exactly what the policy gradient allows us to do. And the key idea, the thing that enables the policy gradient to do this, is that, of course, the policy gradient is taking the derivative of an expectation. And when you take the derivative of an expectation, then what you can do is you can simply consider the derivative of the probabilities of all the samples rather than the actual forward dynamics function. If you look at the regular kind of backprop through time gradient, then you see something more like what you'd expect from the chain rule. You see a product of a whole bunch of Jacobian terms. So you have the derivative of the state at time t with respect to the action at time step t minus 1. Then you have the derivative of the action at time step t minus 1 with respect to the state at t minus 1, et cetera, et cetera. All of that multiplied by the derivative of the reward at state S. And of course, if your state is not continuous, if your state is discrete, this doesn't even make any sense. And if your state is continuous, but your time horizon is very long, this will be very ill-conditioned. Now the funny thing is, okay, there's a little bit of a detail here that I've kind of obfuscated, which is that one of them is for stochastic systems and the other is for deterministic systems. But you can actually modify the regular kind of backprop gradient to handle stochastic systems using something called the reparameterization trick, which I won't cover in today's lecture, but it is covered in the variational inference lecture that you'll watch online. So there's a way to turn this backprop thing into something that can handle stochastic systems as well, at which point the backprop gradient and the policy gradient are in fact calculating the same gradient, but they're just doing it differently. And because they're doing it differently, they have different trade-offs. The trade-offs are things that you guys might have already kind of guessed from before. So the policy gradient does not backpropagate through time, but it pays a price. The price that it pays is very high variance. The backprop gradient doesn't pay that high price in variance, but it has to contend with very poor numerical conditioning if you have very long horizons and Jacobians with eigenvalues that are not 1. So there's a trade-off. But the nice thing about the policy gradient is that the high variance can be reduced if you take more samples. Usually this is a problem for us because usually we would say that samples are kind of expensive because you have to go and interact with the real physical system. But if you have a model, generating more samples is simply a matter of paying more compute. You can in fact do it in parallel. You can have giant batches of 10 million trajectories all being rolled out at once through your giant neural network model, and then use those giant batches to get a very good estimate of the policy gradient. So the policy gradient can actually be more stable if you use enough samples because it doesn't require multiplying together lots and lots of these Jacobians. And if you want to learn more about this, there's actually some more detailed analysis in this recent paper from 2018 that actually studies this in more detail and actually argues that in many cases, even if you can use a backprop gradient, the policy gradient, the so-called score function gradient, might be preferred. I'm not going to really talk about this kind of approach in more detail because it's really very straightforward. You just train up your model. It's essentially the approach on this slide, except that instead of step 3 being backpropagate through f into the policy, step 3 is now run policy gradient with huge numbers of samples generated by your model. So you just change step 3 to use policy gradient for many iterations using synthetic data, and that's basically the method. Okay. So that's the idea. Now, this idea is nice because it overcomes that kind of poor numerical conditioning, but it has some other issues. In fact, the issues that it has actually also get exacerbated as you have longer and longer trajectories. Does anybody have any hypotheses about what the issue would be? Yeah.
Is it like if your model is inaccurate, the longer your trajectory is, the longer you will deviate from whatever the true value is?
Yes, exactly. So the answer was, well, if your model is inaccurate, and your model is always inaccurate, let's face it. If your model is inaccurate, then the longer you roll out your model, the more those errors compound. So if your model makes a little small mistake at the beginning, then it'll make a slightly bigger mistake at the next step, and a slightly bigger one, a slightly bigger one, a slightly bigger one, a slightly bigger one, and then eventually just produces something that has no bearing on reality. So if we're going to say that, well, we'll use policy gradient and we have a long horizon problem, we want to do it for long horizon problems because otherwise, for long horizon problems, this backprop gradient really explodes, so we'll use the policy gradient. But now, in order to use the policy gradient, we have to roll out our model for a huge number of steps. And even a model that is very good, if it's even a tiny bit off, if you roll it out for enough steps, eventually it'll produce some garbage there at the end, and that will cause your policy gradient estimate to be nonsense, no matter how many samples you take, simply because your model is not good. And this is a general trend that we see time and time again in model-based RL, that while it's generally not too hard to get accurate models on relatively short time scales, getting models that are very good for extremely long horizons is tough. So it'd be very nice if we could do something like this, if we could use model-free optimizers, but not have to roll out our model for extremely long trajectories. So this is where the general category of what I'm going to call DYNA-like methods comes in. So DYNA is a particular kind of hybrid model-based model-free algorithm proposed in this paper called Integrated Architectures for Learning, Planning, and Reacting Based on Approximate Dynamic Programming. You know, back in the day, integrated architectures and dynamic programming were really cool things, so you wanted to put that in your title. So these days, you put other buzzwords in your title, but same basic principle. And what DYNA is, it's essentially an online Q-learning algorithm that performs model-free RL, but also uses a model. I'm going to describe the actual DYNA algorithm, and then what I'll describe is a kind of generalization that has been more commonly used in recent algorithms. So the classic DYNA algorithm looks very similar to online Q-learning. In classic DYNA, it's an online procedure, so every single time step you're going to follow this process. You're going to start with some state S, and then you'll pick an action A using an exploration policy. This is just like in Q-learning. In Q-learning, you just pick an action using whatever your exploration policy is, typically some kind of like epsilon greedy thing, something that kind of uses your latest Q function but adds some randomness to it. And then you'll observe the next state S prime and the reward. So that gives you your transition S A S prime R, just like in online Q-learning. So far this is exactly the same as Q-learning. And then what you're going to do is you're going to use this transition to update your model. P hat S prime given SA, and you'll also update a model of your reward. If you know your reward function, you can skip this step, but in general, if you don't know your reward function, you should also learn a function approximator for that. And then in step 4, you'll do the same thing as in Q-learning. You'll just use this transition to update your Q function. So far, we haven't really used our model in any way, and except for step 3, this is exactly online Q-learning. But now we're going to do the new thing. We're going to repeat this little loop for k times steps. Why k? Well, because you can do 1, but k is more general. And here's what you're going to do. You're going to sample some state action pair from the buffer of past states and actions. So you'll just say, OK, now that I've taken this step, let's rewind back to something I saw before and pull out an SA tuple. And then you're going to do a Q function update on that old SA tuple, but you're going to calculate the expectation, the target value, by using your model. So as your model gets better and better, your estimates of this expectation get better and better. So essentially, you train on your latest transition, then you go back in time, load up some old transitions, use your improved model to predict what the distribution of next states for that old transition would have been, and then train on those as well. Now, at this point, many of you might be thinking, well, OK, there's like some arbitrary decisions going on here. Like, for example, you could just sample a state from your buffer and then sample the action from your policy. Why k? Why not have an outer loop around this? You could use the model in this expectation and in this expectation, or just one of them. So there's like a lot of choices to be made. And in many ways, the particular recipe in the original DYNA algorithm is a little bit arbitrary, but you can sort of see the general gist of the idea, that you're going to use your model, you're going to improve your model every step along with your Q function, and then the model will give you better estimates of expected next step Q values for all of your past transitions, and that will allow your Q function to get better and better as your model gets better. So that's the basic recipe of the classic DYNA algorithm. Does anybody have any questions about this?
Where are we using the model?
Where are we using the model? We're using the model to compute this expectation. So in the target value, you have an expectation over the next state. When you actually took that transition, you received a sample of the next state from the true dynamics, but your model can hopefully give you better estimates of that whole distribution, which will give you a better target value. OK. So now what we're going to do is we're going to generalize this DYNA recipe into a kind of a class of DYNA-style algorithms. And these will be a bit more representative of what we actually see in kind of modern deep RL methods. So the general DYNA-style recipe, which is kind of a generalization of the classic method on the previous slide, is this. You collect some data. You collect this data however you want. And this data consists of some transitions, S, A, S prime, R. So you could take one step, or you can take a million steps, whatever, collect some data. So there's your data. Step 2, learn your model using that data, and optionally also learn a reward model. And then step 3, repeat this k times. Sample some states from the buffer. So from that data that you collected, maybe you sampled these orange states. Choose some action at each of those states. And you can choose that action in a variety of ways. So the classic Dyna algorithm would just pick whatever action was in the buffer. But you can also pick the action from your policy. Or you can pick the action at random. You can pick the action however you want. And then simulate the next state using your model. So sample the next state from your model, given the state that you chose from the buffer and the action that you chose according to whatever strategy you want. So that gives you a little transition from each of those orange dots. And then train on this transition, on the synthetic transition where S was from the buffer, A was chosen according to your strategy, S prime was obtained from your model, and R was obtained from your reward model. You can train on this right away, so you can sort of get your transition and consume it immediately, or you can squirrel it away in your synthetic data buffer and then do something more like an experience replay strategy. Both would be totally fine. Optionally, you don't have to take just one step, you can take multiple steps. And that's okay too. So if you believe that your model is good for a couple of steps, take it for a couple of steps, and then you get even more varied data. So the nice thing about this kind of general recipe is that it only requires short rollouts from your model, as little as one step, which means that if the errors from your model compound, this might not be nearly as big of a deal with this type of recipe. And you still see very diverse states. So because you're actually branching from all of these states in your buffer, you can do some training on states that were not actually seen in the real data, but are kind of similar to them. So this is the high-level recipe for actually a pretty broad class of modern model-based RL methods. Here are a few examples. There's some paper references here at the bottom. You can read up on those. And basically, for these three, they all follow this kind of particular instance of this recipe. So they take some action, observe some transition, add it to a buffer, sample a mini batch from the buffer, use that mini batch to update the model, then sample some other states from the buffer. For each of those other states, perform a model-based rollout using whatever the latest policy is. So that kind of produces these little mini branched rollouts. And then they use all the transitions along these rollouts to update the Q function. And the differences between these different methods are in terms of whether they train together on model-based and real-world rollouts, or just the model-based ones, or just the real-world ones. There's also a difference in terms of whether you use these rollouts to estimate target values, or whether you also use them as the current state in action on which to actually train the Q function. So there's a variant on this recipe where you use these little rollouts to get better target values, but you only ever update the Q function on the real states. And there's some trade-offs about whether you should or should not do that. A question?
So there we have potentially three models, three architectures for the model, the reward, and the Q function.
Yes.
So doesn't it run a problem of when you're optimizing these three things in sequence?
Right. So the question for those of you that didn't hear is, there are kind of three separate function approximators here. There's the Q function, the dynamics model, P hat, and then potentially also the reward model, R. If you're doing actor critic, you also have a policy. So you might have as many as 4. So don't you have a problem because you're sort of optimizing these things and they all kind of interact with each other? They do interact with each other. In practice, for this type of method, it doesn't tend to be that bad because you would typically train your model and your reward model on all the aggregated data seen so far, which means that the effect of a changing Q function on the model is heavily damped. So your Q function does influence the data that the model sees, but because you're aggregating all the data, a kind of a moderate change in the Q function won't radically change the data seen by the model. So in practice, the model doesn't get destabilized by the Q function. And then as a result of that, the Q function doesn't really get destabilized by the model either, because since the influence one way is limited, the influence the other way gets limited too. So for some methods, like actor-critic methods, that dependency between the two models can be really delicate. So the dependency between a policy and a Q function for actor-critic methods can cause a little bit of kind of chattering back and forth. For model-based RL, it's typically not nearly as much of a problem. Okay. Why is this a good idea? Well, it's a good idea because we have short length rollouts from a model, but we can still greatly increase the amount of data that we have for training the Q function. Why is this a bad idea? Well, let me ask you guys. What do you guys think might be some bad things about this? Yeah.
Initially, when the model isn't good, you might corrupt. You get a bunch of bad data.
Yeah, so one possibility is that maybe initially your model is no good, and you generate transitions from it, you use them to train your Q function, and your Q function just really tanks from that, and then you have a garbage Q function. So that can definitely happen, and you do, in practice, need to be quite careful with these kinds of methods to make sure that you get a good model. And sometimes sort of a very delicate choice to be made is how long you choose those rollouts to be, depending on how much you trust your model. This last paper called When to Trust Your Model, appropriately enough, actually discusses this issue and actually derives some bounds on how long your rollout should be for a given level of improvement. Any other hypotheses? Yes, Sasha?
It feels odd to use the model to train the Q function because, like, if you're working from images or something, they might look very differently. Maybe it gets blurry.
Yeah. Right. So this is sort of the tough criticism. It might seem like it's a little weird to use a model to improve your Q function because, you know, for some things like image pixels, it might actually be harder to train a good model than it is to train a good Q function. And this is actually, like, you know, to be perfectly upfront, this is kind of one of the bigger mysteries for this class of algorithms, is that it seems very hard to precisely disentangle the kind of situations where learning a model is easier than learning a Q function, especially since the Q function is, in a sense, a kind of model that predicts future rewards. While there are a few results that kind of go either way as far as when is it a good idea, when is it not a good idea, in general, it's probably fair to say that people don't really understand this as well as maybe we should. There was another comment back there?
I had a question.
Mm-hmm.
Is there any drawbacks associated with having rollouts that are too short?
Yeah. So the question was, are there any drawbacks with making these rollouts too short? Well, the shorter you make them, essentially, the less you benefit from your model. So if you make the rollout of length 1, you're kind of incurring the least error from your model, but you're also seeing the least new stuff. So the trouble is that if you want to change your Q function a whole lot without collecting a lot more data, eventually you basically run into this problem where the data you collected before in step 1 is just too different from what you would see if you were to follow the greedy policy with respect to your current Q function. So while you can train up your Q function really well on that data using these one-step rollouts, when you actually run the policy with respect to that Q function, you see totally different things that you're unprepared for. All right, so that's the end of the kind of model-free plus model-based methods. So we'll take a little break at this point. We'll reconvene when that clock hits 10:55, and then we'll discuss local policies. So see you in about 3 minutes.
They're trying to reschedule, so one of them will have during lecture, the other one. First come, first serve.
In college, they typically make you sit like with your space apart.
Yeah, like they just want to like that. If they had it,
Yeah.
to each other, but typically
People are sitting by me because it's like I know they're peaking.
Is there one asking me? You can come up.
MPC. MPC is also closed loop control.
Yep.
You're observing the state
Yeah.
and then.
Yeah, so that's kind of a delicate one. It is, like, people call it either closed loop or not closed loop. You kind of don't want to call it open loop because it's really not. But there's a difference because in MPC, like, you can do MPC with either closed loop planning or open loop planning. So LQI actually does do closed loop planning. But you can also do MPC with open loop planning, meaning that when you plan, you don't realize that you'll be allowed to replan. And that can be computationally advantageous, so you can use, you know, some kind of like random shooting method or something. And then you do replan every step, but you don't plan for replanning every step, which means that you might decide to do kind of overly cautious things. Like, you know, for example, if you go back to that algebra quiz, I can tell you have two choices. You can either take the algebra quiz, or you can receive a grade of C+, right? So the open loop thing would always choose to go for the C+, because it knows that if it like just takes that action, it'll get the C+, whereas if it has to commit to a plan for the quiz, it might get all the answers wrong. But if it knows that it's allowed to replan, then it might realize that, oh, actually I should take the quiz, because even though I don't know what it will be, once I see it, I'll do well.
It can be the case where you make the feed-forward plan and make the questions for the quiz, but then after I see something, I adapt.
Yes. So MPC would do that. The trouble is that if it's given an option to go for this like situation where it doesn't know what will happen and will have to replan, and it doesn't know that it will get to replan, and has another choice where replanning is not necessary, it'll go for that other choice, even though it's suboptimal.
Ah, okay, but then you have to say, okay, he's not allowed to replan, right? But in reality, you can allow it.
Well, yeah, but then the optimizer that's
pay more computation.
yeah, you have to pay more computation for the optimizer to realize that it gets to replan.
Yeah,
so like Monte Carlo tree search understands that it'll get to replan. LQR locally understands, but something like random shooting just doesn't understand that. So it would always opt for the conservative option.
Okay.
All right, we're going to resume. So before the break, we talked about how there were these two classes of model-based policy learning methods that we'll discuss. The first one, which we covered before the break, was to use essentially model-free RL algorithms together with the model. The second class is to use simpler policies that are simpler than neural nets, and that are amenable to optimization methods that overcome some of the difficulties of backprop through time. And that's what I'll discuss in the second half of today's lecture. So let's go back to this slide that we saw back when we talked about optimal control. So as a refresher, this would have been the Wednesday the week before last. We saw that if we are willing to mentally substitute X for S and U for A, we could and minimize costs instead of maximizing rewards, then we could rewrite our control problem as an unconstrained optimization. So we could say, well, your control problem is to minimize your costs such that your next state is given by your dynamics F applied to your current state in action. And because the constraint is an equality constraint, you can substitute that into your objective and get a completely unconstrained objective, which is a mess to write out, but not actually all that bad. And that's what that second line shows. And then we talked about how you could optimize this objective, and all you really need in order to do that is the derivatives of F and the derivatives of C. And while first order optimization, standard gradient descent, does not necessarily work very well, we saw that we had this very convenient dynamic programming procedure that we could derive called LQR, or iterative LQR if you have non-linear dynamics. And that method actually corresponds to kind of an efficient way to apply Newton's method to this kind of problem without ever having to calculate Hessians that are on the size of the whole trajectory. So the only matrix inversions in LQR were on the size of the dimensionality of the action space, making the whole process linear in the time horizon. That's very, very convenient. So now we might think, well, LQR worked so well, it allowed that little hopper robot to stay upright, it allowed the humanoid to stand up and kind of waddle around. Seems really promising. Can we use something like that with learned models? And the answer is that we can. But we don't get complete global neural network policies out of doing that. We get very local policies. So here is the idea. The main thing that we're lacking in the standard reinforcement learning setting is knowledge of these derivatives, df dx and df du. So if we can learn our model and we can somehow get these derivatives out of it, then we can perhaps use the same LQR procedure and get local policies. So here's the idea. Let's just fit df dx and df du around the current trajectory or policy. Very simple. We have some current policy, doesn't really matter what it is. We'll run it. Hopefully the trajectories it produces are sufficiently close together that you can just take those trajectories and fit linear dynamics. Just literally estimate f as df dx times x plus df du times u plus some constant. Essentially linear regression. Do linear regression, you get some estimate for these derivatives, and then plug that into LQR and hopefully get a better trajectory. So you get these linearizations at every time step. Run LQR. LQR actually gives you a linear feedback controller. So as we saw before, it gives you that kx plus little k. So not only does it give you an action, it actually tells you how your action should change in a linear local way around your state. And you can run that in the real world, collect some more trajectories, refit your dynamics, and repeat. That's the high-level idea. So if you have a continuous system that is sufficiently smooth and an initial state distribution that's sufficiently tight that this kind of thing actually makes sense, then you can actually do this. So here is the kind of outline of the procedure. You run your current linear feedback controller, which we're going to turn into a probabilistic controller, as I'll discuss shortly. You get some trajectories, you fit your dynamics on those trajectories, and your dynamics are going to be some kind of conditional Gaussian thing, and the mean of that Gaussian is a linear function. So they're linear Gaussian dynamics, which we know that LQR can accommodate. The only thing we need to get out of these dynamics is A, B, and sigma, but we know from the LQR lecture that sigma actually doesn't affect the answer. So regardless of what your sigma is, you'll still end up with the same controller. So you don't even need to bother fitting sigma. You can just ignore that part. And all you really need is the A and the B. And you have potentially a different A and B at every time step. So it's a linearization per time step. And then we'll just say that A is df dx and B is df du. And then just plug that into iterative LQR like we saw a week before last. That'll improve our controller, and then we just repeat this process. So one question we have to resolve to actually formulate a practically useful algorithm of this type is, well, which controller should we actually execute when we collect data? So iterative LQR produces these x hat, u hat, capital K, and little k. And we saw from the LQR lecture that we can write out the full controller like this, capital K times x. And then the other terms, they're basically just all, they can all be collected into one constant. So it's really just capital K times x plus some kind of constant. And we saw from the ILQR lecture that this u will give you the optimal action at convergence once you run ILQR for enough iterations, but you have to relinearize repeatedly. So at any one iteration, it just gives you an improved sequence of actions. So a very simple choice would be to just say, well, let's just take the good action. So we'll calculate this thing, figure out the optimal action, just take that action all the time. That's not a very good idea because, of course, you calculate your actions under an imperfect estimate of the model. And if you're just executing those actions in open loop, it doesn't really correct for drift. It doesn't correct for small deviations from the state that you thought you would have gotten. So a very simple and slightly better choice is to just always take the action given by the linear feedback controller. Because this big K matrix, that's going to act to stabilize you a little bit around the nominal trajectory that ILQR produced. So you'll basically take the action that you planned, but you'll also have this correction term given by capital K times x. And what that will do in practice is that if you deviate a little bit from the trajectory that ILQR came up with, hopefully your big K will bring you back there. So that tends to work quite a bit better. The problem with this is that it might actually be a little too good. See, unlike in regular ILQR, here we're fitting our A and B matrices, we're fitting our linearization of the dynamics to data. And it's very hard to fit something to data if your data all looks the same. Those A and B matrices, intuitively, they model how the dynamics changes in a local region around a given trajectory. So if all of your trajectories are almost exactly the same, you won't be able to fit a very good matrix to that. Just in the same way that you won't really be able to do linear regression from x to y if all of the x values in your data set are identical. So if you have trajectories that are kind of a little bit spread out, but not too spread out, that's sort of ideal for linear regression, because then they're sort of sufficiently tightly clustered that a linear approximation is good, but broad enough that you can actually fit that linear approximation. If they were all precisely on top of each other, then any line could fit them equally well, which means that you won't be able to come up with the right linearization. And if they're all way spread out, then they're outside the regime where a linear fit is even remotely accurate. So you want them to be a little bit clustered, but not too clustered. So in practice, a better choice is to actually construct a stochastic controller out of the linear solution to LQR, which you can do just by choosing a Gaussian where the mean is the feedback controller from before, but there's a little bit of variance added to it. Now, you can choose this noise actually in many ways. You can choose it heuristically. You can choose it to be, 0.1 times identity. If you want a more principled choice, this is a little bit outside of the scope of this lecture, but it turns out that a very nice choice is to actually choose the variance to be the inverse of the Q function matrix from LQR. The very high-level intuition for this is that the Q function matrix models the local curvature of the Q function. If the Q function is really, really peaked, very sharp, that means that your action very strongly influences the outcome, which means that you don't want to be too random. Like if you're on the edge of a cliff, your Q function is very sharp, so at the edge of the cliff you want to be pretty deterministic because even a small mistake will cause you to go off the cliff. But if your Q function is very shallow, if it forms a very shallow bowl, that means that the value is relatively insensitive to the choice of action, which means that you can afford to add lots of noise without getting really bad trajectories. So for that reason, it actually turns out to be very convenient to set sigma to be QU inverse. But if this isn't kind of readily obvious to you, don't worry too much about it. The important bit is to add some kind of noise to produce a little bit of dispersion among your trajectories. OK, any questions about the choice of controller for collecting trajectories for fitting local models? All right. So now the other bit is the actual fitting of the local model, right? So as I said before, we're going to want to estimate our dynamics locally around the trajectories we collected as a linear Gaussian, and we have to fit A and B. And then we're going to improve our policy. So how do we fit the dynamics? How do we fit this A and B? So we have a collection of transitions, xt, ut, and xt plus 1 from all of our trajectories. A very simple choice is to fit the A and B matrices at every time step using just regular linear regression. And that actually works. So you have you're estimating your dynamics like this, and you're just going to fit AT and BT. You can also fit the noise, but since the noise doesn't actually appear in the LQR algorithm, it actually doesn't matter what it is. So you can just ignore that part. That's reasonable, but it has a little bit of a problem, which is that linear regression requires a number of samples that scales with the dimensionality of your state. So if you have a 100-dimensional state, you'll need a lot more samples than if you have a 10-dimensional state. You can actually do quite a bit better in practice if you combine these local models with some kind of global model. So what you can do instead is you can actually fit your dynamics with Bayesian linear regression. And if you ever have to implement this method in practice, this is usually what you would do. You would fit it with Bayesian linear regression with a prior given by your favorite global model. So you would fit some kind of global model, whatever you want. You can fit a deep net, you can fit a Gaussian process, anything, and then use that as a prior when estimating A and B. And then you can get away with many, many fewer samples. So essentially, the kind of coarse level global information comes from the global model, and the fine details are filled in by the local linear regression. Anyway, this is kind of an implementation detail, but in practice, it allows you to get away with many fewer samples. OK. So that's kind of the gist of it as to how you run your controller, how you fit your dynamics. There is one very important remaining issue, which is that, of course, for most real problems we care about, the dynamics are not linear. So you can kind of imagine that blue line as a cartoon of the linear dynamics that we're fitting, and the green curve as the real dynamics. So locally, the blue line approximates the green curve, but globally, it's pretty far off. So if you run LQR, you get back a better controller than you had before. So maybe this is what your controller thinks will happen. It thinks I'm going to get this blue dotted line. But in the process of doing that, you wander into some region where your linear dynamics is a very poor approximation for the real dynamics. Then when you actually run that controller, you get something like this. Right? So intuitively, the linearization of the system that you calculated via that linear regression is only really good in the local region around your trajectories. So you have to somehow prevent LQR from coming up with a solution that's way off from the region where you fitted your dynamics. And this turns out to be actually very, very important to get this kind of method to work well. So the way that we're going to do this is very similar to an idea that we saw before. We're going to estimate our trajectory distribution for our new controller. And then we're going to try to find some way to keep that trajectory distribution close to the distribution of trajectories that we saw under our old controller. Just like we saw with the trust regions for policy gradient, where we would constrain the KL divergence between policies to keep the resulting state distributions close together. In the same way, we're going to basically constrain the divergence between the controllers to keep the trajectory distributions close together. So if the trajectory distribution is close, then the dynamics will be close also. And what does close mean? Well, close just means that the KL divergence is small. And it turns out that it's actually very easy to constrain KL divergences between two controllers obtained with LQR simply by modifying the reward function to add the log probability of the old controller to the reward. I won't go through that method in detail, but if you want to learn about it, check out this paper. It's a very simple technique. You just add a reward term that says have high probability under my old controller, which basically keeps you close to it. So that's basically the gist of it. Fit dynamics with linear regression. Use a stochastic controller to collect your trajectories, and then keep the new controller close to the old one. And that will allow you to essentially apply iterative LQR without knowing the true dynamics of the system by iteratively refitting it via linear regression. Here is a little animation of that method in action, just to prove to you that it actually does do something. This is a robot learning to stack a Lego block using iterative LQR, essentially. So every time it takes one of those trials, that's a trajectory that it's using to help linearize the system. And when you see it kind of pause a little bit between attempts, so you'll see that in a second. It takes 10 attempts and then pauses. When it pauses, that's when it's refitting those linearizations, updating the controller, and so on. So this is not really like a deep RL experiment. This is just an iterative LQR experiment. OK. So something is happening there where we can get local models and local policies. And we can get closed-loop control because LQR gives us closed-loop control. But it doesn't seem like we've really kind of accomplished the same thing here as we have in all the other deep RL methods, because the controller is only linear. You need to kind of start from a fairly narrow range of initial states. And you need continuous states, and everything needs to be smooth and differentiable, and so on. So in the last part of today's lecture, I'm going to talk about how, if you get these local policies, how you can actually combine them into global policies using supervised learning. And that's where we can actually have the deep nets and vision and all these other things come in. And that will also allow us to kind of develop a general class of methods that are all based around the idea of combining lots of local policies into a single, more powerful global policy. And that turns out to be a useful idea, not just for model-based RL, but actually in a variety of other areas as well. OK, so here's the high-level idea behind this thing called guided policy search. So the idea behind guided policy search is that we're going to use some kind of weaker learner, like a model-based local policy learner, to guide the learning of a much more complex global neural network policy. So we'll do this kind of trajectory-centric reinforcement learning, the little iterative LQR thing. And we'll do it for a number of different initial states. So if you imagine the robot from before with the Lego blocks, I guess this robot has a slightly different task, but whatever the thing that it's doing, you can decompose a more complex task into a bunch of initial states. So maybe you say, well, for the Lego block task, it just needs to succeed in stacking the Lego block from here, and from here, and from here, and from over here. So if you have a variety of initial states, break them up into a discrete set, and then learn a separate LQR controller from each one. The purpose of this is so that each controller is only responsible for a narrow region of the state space, so that local linearization actually makes sense. So you break it up into a problem, into a set of problems, each of which is solvable with local models and local policies. So here's an animation of that in action. And then all we're going to do is we're going to take the solutions from these local policies, and we will use them as training data, essentially for imitation learning. We'll use them as training data to train a single neural net policy that works from all initial states. So if this robot collected a bunch of data of doing this little, in this case, a little toy task where it inserts a shape into a cube, now we use all of that to train a deep net. And that deep net might actually be trained with supervised learning, and it can actually use a different input if we so choose. So maybe we train these trajectories from the low-dimensional state of the robot, but the deep net maybe uses the images from the robot's camera as input, so that it can actually figure out what it's supposed to be doing directly from images. And then you can do things like have actually somebody hold the shape, so the robot needs to use the camera to figure out where it is, and it does the task using the deep net. That's the first kind of high-level idea, but there's a problem with this approach, which is that the particular behavior that these trajectory-centric controllers, these LQR controllers actually do, might not be reproducible by a single neural net. Because these are highly multimodal objective landscapes, and you might have multiple local optima, and perhaps one of your LQR solvers finds one local optimum, and another one finds a different local optimum. They're both successful, maybe they're both good enough, but they can't both be crammed into a single policy. So an important detail to get this kind of recipe to work is to actually close the loop and to say that after you train your global policy, your neural network, with supervised learning to mimic the behavior of each of your local policies, then we have to go back in and re-optimize the local policies to be consistent with the solution that the global policy came up with. So maybe the first trajectory here did the task one way, the second one did it in a different way. When we train a neural net with supervised learning to copy both of those, maybe it's like 51% the first solution and 49% the other solution. And then what we do is we include an additional cost term for these guys to say, do whatever the deep net did. Basically, try to copy the global policy. And because the global policy will break the tie arbitrarily, say, well, I'm going to lean a little bit towards this solution. Then when the trajectory-centric solvers are forced to incorporate that as a reward, they'll all tend to lean even more in that direction. That will eventually break the tie. So in general, by enforcing this little kind of feedback arc and saying, well, let's train the local policies to do something more consistent with the global policy, eventually they'll settle on a consensus, and all the local policies will do things that the global policy can actually reproduce. So here's kind of the algorithm sketch. 1, optimize each local policy, which I'm going to call pi LQR, comma I. The I is for the ith local policy, so there are a number of them. Optimize it on some initial state x0i, so they'll each have maybe a different initial state. With respect to some cost, C tilde ki. So k for the kth iteration, and I for the ith local policy. Initially, the costs are all the same. Initially, the costs are just your task costs, but later on, they'll actually change. So this cost will be modified a little bit to keep the LQR policy close to the global policy pi theta. Step 2, use the samples that were collected from step 1, those samples that we used to fit the A and B matrices, use them to train pi theta to mimic each of the pi LQR. So this is basically supervised learning. It's essentially imitation learning, where you're imitating these LQR controllers to get a single deep net pi theta that tries to copy the behavior of all of these guys. And then step 3 is update your cost function to get C tilde k plus 1i to be the task cost plus some coefficient lambda times the log probability of your global policy. This should actually be a minus because it's a cost. So you want to maximize the log probability, which means you want to minimize the negative log probability. So this modification of the cost basically tells the global policy, or tells each of the local policies, do whatever is consistent with the global policy. And then you repeat the process. And this little multiplier, you can view it as a Lagrange multiplier for a constraint that says at convergence, make sure that pi theta does the same thing as pi LQR. And then you repeat this process. So learn each of the local policies with a modified cost, use those samples to train a single global policy to imitate all the local policies, and then modify your cost to more strongly enforce consistency with the global policy, and then repeat. And if you go around this loop enough times and you adjust the Lagrange multiplier using the appropriate adjustment rule, like dual gradient descent, then you'll eventually end up enforcing this constraint, and you'll end up with all the local policies doing the same thing as the global policy. And then you know that the global policy will be able to actually reproduce them. Yes?
Like, why not just take samples from like the environment instead of your local policies?
OK, so the question was, why not take samples from the environment instead of your local policies? So to be clear, when it says use samples from step 1, these are samples from the environment that were collected by the local policies in order to estimate the linearization matrices. So it's exactly what you're thinking.
So then what's the purpose of the local policy?
The purpose of the local policies is to actually solve the task. Yes?
So do we train the local policy for different initial states?
Yes. So the question was, do we train the local policies for different initial states? So for each initial state, there's a different local policy. And you can kind of generalize this idea to say for every grouping of initial states. So if you have like a little cluster here, a little cluster there, basically the groupings need to be narrow enough so that a single linearization can take care of all the things that start in that group.
So in that case, couldn't you train the supervised learning to identify the clusters? Become a problem of like, instead of training to match the LQR policies, just identify in which region of the
right.
space you are. And
yeah. So the question was, can you just like, basically, yeah, if I were to translate it, like, why bother? Do you really need a policy here, or do you just need a classifier? And it's a very good question. And in many cases, you could actually get away with that. You could say, well, instead of training a policy, just train a selector to pick among the LQR solutions. That will actually work, and there's actually been some work that does exactly this. So there's sort of a deeper body of prior literature on something called trajectory libraries that does essentially variants on this idea. One reason why you might still want to train a deep neural net policy is if you want to also do a kind of an input remapping trick. So one of the things you can do with these kinds of techniques that's very convenient is that you can train in a setting where you have a little bit of privileged information, where you know the true state of your system so that you can do the linearization, but then train your policy on maybe partial observations. So for example, maybe during training, you have an instrumented environment where you can localize all the objects. You use that for step 1. And then in step 2, you train your policy to output the same actions, but condition on maybe camera images. And then you don't need the instrumentation at test time to run the policy. Any other questions? OK. So I introduced this general idea as kind of a way to do model-based RL, where you do local models and local policies for step 1, and then still end up with a deep net in step 2. But actually, this general idea of using local policies and supervised learning to recover a global policy is something that can be used in a variety of other settings beyond just model-based reinforcement learning. You can actually use these techniques for model-free reinforcement learning problems, and it turns out that they can actually work pretty well there also. So to sort of motivate this a little bit, I'm going to tell you about a technique that has nothing to do with reinforcement learning called distillation. And this slide is actually adapted from a talk by Jeff Hinton based on a paper called Distilling the Knowledge in a Neural Network. So this is a technique that originated in the world of supervised learning. And the idea is basically this. This is what motivated the idea. This is not how we're going to use it, but I think the motivation is interesting to know about. So one of the things you can do, if you think back to my discussion of uncertainty estimation in model-based RL before, is you can train an ensemble of neural networks. And an ensemble of neural networks is good for a few reasons. It's good because it allows us to estimate uncertainty in model-based RL. But in the world of supervised learning, it's also good just because it works better. You know, 5 neural networks is better than 1 neural network. In fact, if you want to get really competitive models, oftentimes a good recipe is to take a model that already works really well and then ensemble it. And it'll probably work a bit better. And if you really just want to squeeze as much juice as you want out of your models, that's generally a good way to get a couple extra percentage points on some Kaggle test set. And the problem is that this tends to be kind of expensive. Because before you had 1 model, now you have 10 models. So it takes 10 times longer to do everything. So the problem that the authors of this paper were concerned with, and it turns out they actually solved a much broader problem, but this was the problem they were concerned with, is how can you make a single model that is as good as an ensemble without incurring that 10x cost and compute? But it turns out that what they ended up with is a lot more useful than just reducing compute costs. So the idea was very simple. Take the ensemble's predictions and treat them as essentially soft targets. So the ensemble will make predictions about each of your training points, and the prediction will not give 100% probability of the true label. It'll be kind of smoothed out. So then you can construct soft labels by basically taking the logits from your ensemble, the log probabilities, dividing them by some temperature. You can pretend the temperature is just 1 for simplicity, and then using those as soft labels. So this is the logit, and that's the temperature. So now you might ask, well, what's the benefit of doing this soft label thing? Like, if I have a training set, my training set is labeled. If I'm doing like MNIST classification, I know that the 1 is a 1 because it has a label that says 1. Well, the trouble is that real labels actually don't contain as much knowledge as these soft labels. So here's a picture of the MNIST training set. And let me find a particularly bad one here. Like, you know, if I look at this character, this is actually a 2. But I might think, well, this 2 kind of looks a little like a backward 6, maybe a 0. Maybe it looks quite a bit like a 0, actually. The label, the true label, doesn't contain that information. But the ensemble will tell you that. The ensemble will say 70% chance it's a 2, 25% chance it's a 0, and 5% chance it's a 6. Now you might say, well, that's incorrect. It may be incorrect, but it's actually in some ways closer to the truth, because if you understand that this looks a little bit like a 0, you'll actually get a better understanding of the difference between 2s and 0s. You'll say, well, if you want to differentiate 2s from 0s, don't pay too much attention to these things, because they're actually ambiguous. This is a good prototypical 2, this is a good prototypical 0, and this guy's in between, so don't take the true label too seriously. And there's knowledge contained in that, and if you distill that knowledge into your model will do better. So this was the idea behind distillation for regular supervised neural nets. And if we combine this with the idea from the slide before of using supervised learning to train a single global policy to imitate lots of local policies, we can derive essentially an extension to the world of reinforcement learning, which is policy distillation. And policy distillation has actually been used in a variety of different ways, not just for model-based RL, but to actually distill multiple policies that are all learned with model-free RL into a single global policy. So here's an example of a paper called Actor Mimic, which is from, I think, like 4 years ago at this point. And in this paper, what they wanted to do is they wanted to train a single policy that could play all the Atari games. You can try this in homework 3. I think you'll find it a little bit difficult to do with regular Q learning. In fact, multitask RL of this sort tends to be very difficult, but training an individual policy to play each of the games is not actually too bad. And then once you train a policy to play each of the games, then you can just use supervised learning, just like we saw in guided policy search, to train a single global policy that can play all the games at the same time. And that turns out to be actually much easier in practice than trying to do multitask RL to learn all of the games all at once. So this kind of specialization, allowing each model to specialize to a single game and then distilling to get a single central policy, ends up actually working quite a bit better. So the objective that you use for training the global policy in this paper is essentially just a standard supervised learning objective with these soft labels analogous to policy distillation, analogous to regular distillation. So the soft labels are basically the probabilities from the individual local policies, and then this is just essentially weighted max likelihood. So each action is weighted by the probability of that action under the local policies for the corresponding game. So it's just supervised learning or distillation. It's essentially analogous to guided policy search, but applied to the multitask learning problem. So guided policy search was concerned with making model-based RL work better. This is concerned with making multitask learning work better without actually using any models. Okay, another detail is this kind of feedback edge, this edge that says once you train your global policy, go back in and modify your local policies to make them more consistent with the global policy. That can be applied to the policy distillation setting as well. So in the same way that it allowed us to modify the local policies from that LQR procedure to be consistent with a global policy, you can also use it to modify neural net local policies to be consistent with a global policy, and that also works and that also actually helps. So this is basically the recipe behind something called divide and conquer reinforcement learning. The algorithm sketch is actually very similar to guided policy search, except I'm going to replace all my X's with S's again. So you optimize each local policy, which now is a deep net instead of an LQR policy. So you optimize each of your pi theta i's on their corresponding initial states with respect to reward r tilde. Then you use the samples from step 1 to train a global policy with supervised learning. And I apologize that I keep switching between S's and X's. I'll fix my LaTeX format file next time. And then step 3 is you update your reward function, just like before, to be the task reward plus the Lagrange multiplier times the log probability of the global policy to keep everybody consistent. And this actually also turns out to work quite well. It allows you to solve some tasks that have kind of a little bit more complexity in the initial state. So I'll show a little cute video to conclude this. So here is a single multitask learner. This is a trust region policy optimization algorithm, and it's supposed to catch this ball thrown from many different vectors. And you can see that it doesn't succeed very often because it's basically trying to solve a little too hard of a task. With divide and conquer, you have a different policy for sort of each quadrant from which the ball can be thrown, which is then distilled into a single global policy that can catch the ball from any location. Here it's trying to pick up the little cube, and the cube can start off in different places. So for a regular multitask learner, that turns out to be pretty tough. But if you train for picking up from different locations, so you train one policy here, one policy here, one policy here, and then distill into a central global policy, that ends up being quite a bit easier, and so on. Okay, so if you'd like to read more about this general idea, here are some references, both on policy distillation and guided policy search, so you can read through those and get kind of an overview of that area. And that's basically it. So I'm out of time, so I'll conclude the lecture now, but if you guys have any questions about this, please feel free to come up after lecture and ask. See you all on Wednesday.
Yeah, I kept forgetting one. It was pretty much just like a bunch of